So good morning, everyone. Today we're going to talk to you guys about a device that changes color based on your blood alcohol concentration level. I know you guys are probably thinking that there's many devices out there in the market, that, such as like the breathalyzers, that you can purchase to like actually figure out your blood alcohol level. But here we're going to present to you guys something different that's integrated with nanotechnology. So before we proceed with this presentation, I want to ask you guys a question. Who here has gone out for like drinks to a bar just to like watch a Super Bowl game or to hang out with friends? I'm sure there you go. So we have people that go out there. So now I want to ask you the bigger question. Have you ever like driven after going out to the bar, after having a couple of drinks? Have you ever driven after that? You must have, right? And you're not unsure if if your blood alcohol levels are above the limit or they're not. You're not sure because there's no test unless you have a breathalyzer on you. So here we're trying to present you a solution for that. So the motivation for this project was that impaired driving is a major concern for road safety. In 2015, police reported almost 72,000 cases of impaired driving, which is almost 72,000 that could result into like car crashes or even lead to like potential death from the car crashes, right? That's a lot of people dangers on the road. Another motivation was that existing methods of BAC, they're costly and bulky. So you could go to Best Buy, you could pick up a breathalyzer for around $50 to $100. A reliable one, that'll cost around $50. You could pick one up, but those are pretty big, and so you want something feasible, you want something less expensive in that sense, right? I'm looking at you because you're pretty much interested in this presentation. Another motivation was that we conducted a survey with 5 bars in Waterloo. Around 100 individuals were surveyed. From the survey, what we got was 80% of the population that were surveyed, they wanted, the people in the bar, they wanted like a cheap and feasible device that they could actually test out this alcohol in them after having a few drinks. So therefore, we present you this saliva-based alcohol test. So for our deliverables, our primary deliverables were ease of use. So you want to have the end user can easily use this device. Ease of interpretation of results. So pretty much once you see this device, once you put it in your mouth and you take it out, you should be able to see the results right away. Right, easy to interpret the results. And safety. So all the chemicals that we're using in our products, they're actually non-carcinogenic, and it's proven out there with literature. Secondary deliverables were speed and cost. So once the user actually puts it in the mouth and takes it out, we want within a minute or two, or even seconds, we want the user to know, oh, I'm not allowed to drive after it because I've had this much alcohol. And cost, we wanted to minimize the cost also in our product because we don't want our thing selling at $50 like a breathalyzer. We want to be really cheap in the user's perspective. And our tertiary deliverables was ease of disposal, so biodegradability. We don't want to harm the environment also. Next. Yeah. So then after looking at the deliverables, we actually transformed them into functional specifications. So ease of product use, we actually made a strip that's 3 centimeter in length and 1 centimeter in width. So pretty much 1.5 centimeters squared of the area is where the user actually put the strip in their mouth to carry out the test, and the other 1.5 centimeters where they hold it. So ease of product use. And then we try to optimize speed versus cost of BAC detection. In this, we try to use materials that would make the reaction faster, but we don't want to increase the cost also, right? We're still trying to minimize the cost. The next is ensure that the product is FDA compliant. So all the reagents that we're using in our products, they're all FDA compliant so that it's actually safe to use for the end user. And ease of disposal, which is biodegradability again. Next. So in order to validate our design, we must verify like the saliva alcohol concentration correlates to like the blood alcohol concentration. We want to have the same correlation there, because the breathalyzer, that's what they use. They use like the breath, and then they correlate it with the blood alcohol concentration. We also want to verify the underlying mechanism behind colorimetric analysis appropriately detects like alcohol in a minute concentration in saliva. The small level of saliva, you want to be able to like detect get your results, and also verify safety for human use. So by looking at this chart, you can see that by looking at this chart, although like measuring alcohol content, although measuring alcohol content through blood is the most accurate, measuring through saliva also gives you a high enough accuracy without having to use like any intravenous or messy methods. So saliva test is actually accurate. So this graph actually proves it. If you look at saliva, it's right up there with the blood, 0.37 or 0.043. It's really correlated with the blood alcohol concentration level also. So that validates the route of detection. The next validation was the colorimetric analysis verification. In order to validate the colorimetric analysis, we looked at proven literature. So for a fixed amount of TMB, which we use in our product, as you increase the enzyme's concentration, which is a peroxidase in this case, you achieve optimal oxidation. Meaning for a product, color change will happen faster. So it's giving you it's faster results you're trying to see in this sense. And safety, all the safety and toxicity, all the reagents we're using, they're all safe to use. So our engineering design specifications. So pretty much we transformed all our functional specifications into design specifications, and we grouped them into two different categories: solution composition and solution deposition and drying. For solution deposition of the design specification, we actually referenced a few literature patents out there that have already proven this technology, and then added to that. So we have like the basis of what to work with. For the solution deposition drying, we actually used PET polyethylene. But then at first when we used PET actually, when you're using, it's not, first of all, it's not biodegradable, so that does not address one of our deliverables. So we switched to filter paper instead, which is actually cheaper and it's also biodegradable. Right? And these are the materials. So for our basis of design, we wanted to make it cheap, and so then we're trying to limit the amount of material we're using in this sense. So then pretty much after doing all this cost analysis with all these materials, it came up to like 10 cents a test, or 10 cents for a strip, which is very cheap and considered compared to like a $50 breathalyzer. These are the materials, and now we'll talk about how we're going to go about synthesizing this product. Oh, yeah.
Okay, so let's take a look at the synthesis. So we studied literature to determine the appropriate reaction mechanism that's necessary to create the color changes that we require. So based on the materials we listed just previously, here's how they behaved in our wet chemistry lab. So in the initial trials, we see here the enzymatic solution and the colorimetric solution that is required for our reaction to take place. So in the initial trials, we can see here in the third vial on the screen the results after adding ethanol to the mix. So the initial trial was run with a much higher ethanol concentration. Therefore, the color change did not provide us with any useful information as of yet. We had to devise a strategy as to how to carefully measure color change with respect to blood alcohol concentration to make this more meaningful and actually create observations. So if you recall the validation section, with varying HRP concentrations or enzyme, we achieve the same color for different amounts. So the only difference seen here is the time to develop the color to the right on the right picture. Therefore, this picture on the left is what our solution looked like shortly after adding ethanol. The right is after a given elapsed time for both to react fully.
They approach the same color. That's what he's trying to identify.
So colorimetric solutions with varying amounts of TMB are shown here. A pH paper is used to show that the solution is neutral, therefore to preserve the integrity of the enzyme so that it does not die. From the varying amounts of TMB in the last slide, we produced color profiles for each amount of the TMB based on varying ethanol concentration. So shown here is the enzymatic and the colorimetric solutions with 10 milligrams of our TMB to generate a color profile from 0.02% ethanol to 0.1. Again, the same thing with 20 milligrams of TMB. So you see a more prominent color profile being generated here, as well as for 30 milligrams. So obviously the color profile here is a little bit inconsistent. It's hard to tell exactly what color corresponds to which alcohol concentration. At 40 milligrams of TMB, as you can see for 0.06% in the middle alcohol concentration, the color was not developing properly despite performing consistent trials. So therefore, the profiles generated under 40 milligrams were discarded. Until we finally reached 50 milligrams of TMB, we can see a pretty progressive, clear color gradient being performed. So further characterization was performed using this amount in our synthesis. So visually, it was determined that the best color profile was generated for this specific amount. The corresponding solution and paper color profiles were generated, as shown above, for varying concentrations of ethanol. UV-vis analysis was performed in the characterization. As you can see, these are other representations for the solution and paper-based. And so for our characterization, we produced curves at 630 nanometer peak intensity for all TMB samples. So we can see a clear progressive color gradient, again, for the 40 and 50 milligrams of TMB. They're smoother curves. And here they are isolated. Next slide. Here they are isolated. So obviously, we see a smooth curve for 40 and 50. However, 50 gave us a better visual representation, which would be perfect for a product. Here is the absorbance curve, which shows a progressive increase in absorbance corresponding to greater color intensity as the ethanol concentration increases. So this trend is expected and was the most pronounced among the 50 milligram TMB samples, as I said earlier. So in conclusion, we've synthesized a saliva-based blood alcohol test based on a color gradient for interpretation of results. The solution is biodegradable. It's cost effective and it's fast. So you could see a result in under 2 minutes, possibly around a minute. This is perfect for the setting of a bar or a restaurant where you want to know the results now before you hop in the car. All the materials are safe. They're all FDA compliant. So this provides great benefit for hopefully consumer use. So as a recommendation, obviously, further analysis has to be performed to contrast performance with existing market alternatives. So comparing that to an electronic breathalyzer, urine, blood, and other saliva tests that are out there right now, because there are some that have been researched that are already out there for use. As well as a design for manufacturability is needed to investigate the viability of this synthesis method for a mass manufacturing setting. So if we were to produce many of these tests, again, for consumer use. And as well as shelf life, because we want to make sure that all the integrity of our test is maintained while still being on the shelf in stores. Thank you for listening to our presentation, and now we'll take questions.
So does it test on a gradient of color?
Yeah,
Based
so
on your blood alcohol level?
so basically, watch out.
It's not just
Yeah, so
blue or no color.
no, so we kind of flew by the slide, but just 1 second. It might be distorted because it's scaled out, but basically what you saw in the vials. Oh.
Oh,
So is it working now? Okay, hopefully. So basically what you saw before previous was the color gradient in the vials, right? So that's kind of indicative or illustrated via the first line. Okay. What we did from that was we did that to kind of verify that it was going to be progressive. So we translated that to paper, as you could have seen here, right? So on paper, it's not as linear, but that obviously is a depiction of the absorbance curve. So as you can see, some of the absorbance values, or the lines, fall close to each other. So that is going to produce a color that's equivalent to, I would say, the profile next to it. So you're going to have a harder time depicting between 0.02 and 0.04, but that's fine, because once you surpass that, that's when you start to get problems with like legality, right? You can get a DUI. So that was good in our sense. So when we translated it to paper, as you can see, that's the gradient on the bottom. Okay. As the test progressed with time, it becomes more apparent between 0.04 and 0.06, which is second from the left and the center. But basically, this would be handed to you or kind of given to you with the test. So when you were to do it, you'd have it adjacent to it, so you could compare the color. Similar, yeah. Yeah.
Can I ask you how, let's say you can really reproduce it to a product.
Mhm.
So what is the format of the test? Is it like a piece of paper that
Yeah.
you put in your mouth, or is it like a paper because you say you need a solution, so somebody to speak out the Sarvagya?
Oh, no. So it's funny you mentioned that, because the whole concept of the design, or like the idea, was driven from like litmus paper. So you just want something that's easy to, like a strip, and then you would, in theory, lick it, right? The problem is, like, we can't verify that you can lick it for the symposium, because we don't know technically if it's safe. You don't want to lick something with chemicals on it. But as I mentioned to someone else, like, it's like licking an envelope. People don't really think about licking an envelope and what's on it. They just, oh, I'm going to lick it and go. So as long as it's certified and it's okay, for the use case you're suggesting, yeah, you'd want to lick it and then have the color produced.
You have a bottle of whiskey, say?
Pardon?
You have a bottle of whiskey on the board?
Outside, yeah.
Yeah.
Couple of shots.
We want to test it with that, but obviously we can't bring liquor to the event.
How does saliva, testing it using saliva compare as far as accuracy is concerned, using urine?
Oh, urine, okay.
Is it more sensitive or more accurately?
I would, like, I honestly haven't researched into that. We can look at the table that we have. I know from literature, because the common question is the saliva map to blood alcohol, right? In literature amounts, it's off by a fractional amount, so it's very close. So that's no question. In terms of urine, we have this. Urine's at the bottom. Obviously, it's untested for the lower time frame, but it seems to be in reasonable,
Relation with the blood.
it seems to be proportional with the blood alcohol, though saliva seems to be closer.
Okay, yeah.
Now, obviously, we didn't dive into that because we figured the ideal use case for this product was if you were to be paying, right, and the waitress was to give you the debit machine, and you were like, okay, I have to test something before I go out just in case I want to call a taxi. You want to be doing it on the spot, right, immediate, so you don't have to wait 10 minutes. You don't have to go to the bathroom and follow something else, right? Because then you're not, realistically, you're not going to take that out of the bathroom either. So you want something that's on demand, that's not non-invasive. Any other questions? Do you want to ask a question? Oh, sorry to interrupt.
No, that's fine. So your color, or the color that changes when you expose it to ethanol,
Yes.
it's based on the concentration of ethanol, and it also depends on how much enzyme loading you have.
No, so that's where one of the things we kind of understood is when we went through the design. Basically, the reason we separate it into enzymatic solution and colorimetric solution is to identify that with the enzymatic solution, basically you're playing with how fast you want to generate the color change. The color change is a result of oxidation. So you have the target molecule you're sensing, right? You have the one enzyme that converts it to something that's easy to use. So we convert it to peroxide, okay? We take the second enzyme, and then we take that, which acts as a electron donor, and then the substrate acts as a proton donor. We oxidize the surface, and then more oxidation results in more color. So when you see this plot, forgive me for taking too long. Am I going back?
Yeah, here you go.
It's validation, okay, right here. So when you see this plot, right, what's happening here is we're varying the amount of enzyme. So with a fixed amount of peroxide, which in this case you'd be converting ethanol to peroxide, with a fixed amount, you saturate your absorbance. You'll hit a peak value. But depending on how much enzyme you have, you'll get there faster if you have more. So we had to play with that in order to deliver a test that's obviously cheap enough, because as he mentioned, with the materials list, the enzyme is the most cost demanding, okay? So it's the most priciest material. So you have to kind of limit that in order to deliver the spec for the user. If it's too long, no one's going to use it.
Yeah.
But obviously if you use too much, it's too expensive.
But then doesn't your color change depend on how much of this oxidation that happens, or the electron transfer that happens?
Yeah, but in theory, you have enough TMB to be oxidized, right? So when you approach maximal amounts, I'm sure you could surpass 0.1 and still keep oxidizing, right? Because you have enough substrate. The enzyme is reusable, so it'll be active, right? As long as you have active units, it'll catalyze the reaction, and then it'll pop off and then jump onto the next molecule. But once all the molecules are converted, you can't go anymore, which is kind of indicative of this top line. Got a question?
So, like, people who use this, do they have to carry around a chart now? So after they're tested, they have to like compare it?
No, so if you imagine, if you could pull, let's see if we can go back to the strip. Okay, just 1 second. I believe it's right,
Keep going, keep going.
I know, it's right at the bottom. Give me a sec.
Yeah.
Okay, right here. So you heard us talk about how we have like an active area and a holding area. Okay, ideally what you want to do, have you ever used pH paper? Litmus paper?
In the
You
lab.
have, right? You know how they have that container and it gives you the color like on top, and then you hold the paper next to it? Something along the line. So say you had the test, you really didn't want, like, to ensure that it was okay for you to use. Say you had something you peeled off of it to expose it, so now you can actually test. That thing you peel off could have the colors on it. So then you could hold them, yeah, so you could hold them next to it and be like, oh, okay, I'm good. That makes sense.
Everything's given to you.
Yeah.
Yeah.
That's the whole foundation of the design. It's basically like, as human beings, we're not responsible, right? So you want everything to be provided to you so you can make the best decision, because we're not going to go out of our way to be like, oh, I feel fine, but why should I test, right? Now you have the option to do it. You have no reason not to. Okay?
Thank you.
Thank you.